Okay, students, good morning. Okay, good. 10 of you here. Okay, we just another one. Iman, Okay. Give another 1 minute. Okay, hope I start the recording. Yeah, so today's lesson is going to be about Doppler effect. Okay, so we still in wave, and I think this is the. I think today we see how we able to finish this topic. I think so far what you learn in wave, we learn about something new stuff. We learn about wave. First thing you learn about wave is of course the amplitude, frequency, period, and yeah, the three. And something new you learn is after that is phase difference. What is phase difference? A fraction of a cycle when wave move behind the other. Phase difference, something new. Then after phase difference, we learn about intensity, also something new. Intensity is power over area, watt per meter squared. Four formulas you learn about intensity is what? Intensity is power over area. Intensity proportional to what? Amplitude square. Intensity inversely proportional to what? Square of the distance. And how the amplitude and distance related? Amplitude square is proportional to 1 over square of the distance. These are the four equations. Okay, today's lesson is about Doppler effect. Do you heard of Doppler effect? Anyone?
Yes.
Heard of Doppler effect? What is the use of Doppler effect?
Object comes closer, has a higher pitch. Wait, pitch? Is it no? Is it pitch? Like a higher pitch compared to it's going away. Yeah.
Yeah, correct. So Doppler effect is a phenomenon where the frequency changes. High pitch. Okay, yeah. So Doppler effect, a lot of uses actually. The speed trap, the car, how fast your car moving, the speed trap was tested by using a Doppler effect. And universe expansion, the only proof is the Doppler effect. One of the proof is the Doppler effect. We will come to that. Okay, so Doppler effect, a sound source is moving towards you. How does it amplitude and frequency changes? Okay, so you have to check that. Okay, class, can you please switch off your mic so that no interference? Okay, good. So when I ask questions, you can on the mic and ask me, answer me. Okay, when a sound source is moving towards you, how does the amplitude and frequency changes? How it changes? When the sound get closer to you, the loudness become greater. Okay, when the wave get closer to you, it become more louder because amplitude is bigger. Okay, and how about the frequency? When the sound get closer to you, we found the frequency increases, the pitch rises. Like for example, when an ambulance approaching you, the pitch of the sound get higher. Okay, I think you have sensed that, and it become louder. Okay. So how does the parameter changes when the source is moving away from you? How these two parameters change when it's moving away from you? Of course, the other way around. When it's moving away, amplitude drops because the source is away from you. And of course, frequency also increases. Frequency drops. Less frequency. Okay, the pitch drops when it's moving away. Okay, why that happens? We're going to do quantitatively why that happens. Okay, next, another important question. Anyone? Can you tell me what are the factors affecting speed of sound in air? Two factors. Anyone? What affects speed of sound in the air?
Density.
Very good. Density of the air. Density of the air affects the speed of sound. Any other factor?
Pressure.
Pressure. Pressure. Better answer. The density is like linked to pressure. So the density. And another one is another one. Temperature. Temperature of the air. Okay, temperature of the air affects the speed of sound. More dense the air, more closer the particle, so easy for the sound to transmit. Okay, so the speed of sound increases. More denser the air, more faster the speed of sound. Okay, more higher the temperature, more energetic the air particle will be. So when the sound is transmitted, because it has more energy, so it can transmit the sound faster. So speed of sound increases. So when the density of the air rises, speed of sound increases. When the temperature rises, the particle more energetic, the air particle become more energetic, so the speed of sound rises. Okay, so two factors affect the speed of sound: the density of the air and the temperature of the air. Okay. Okay, so now the last point. What is meant by Doppler effect? It's a phenomenon. It just happens naturally. It's a phenomenon of the change of observed frequency. The change of observed frequency that arises from relative motion between the source and observer. Okay, this Doppler effect happens when either the source or observer move related to each other. You get this Doppler effect. Let's say an ambulance is approaching you. You are standing. The source is moving towards you, so you will experience the Doppler effect. Or let's say the ambulance is stationary and you are running towards the ambulance. You are as the observer. You are running towards the ambulance. You will still will sense the Doppler effect, the rise in frequency. So the Doppler effect happens due to what? Due to relative movement between the source and observer. Either source or observer move, you will get the Doppler effect. Okay. So the Doppler effect considers stationary sound source emits a constant frequency sound. Two observer A and B are here the sound, like this diagram, A and B. The source is at the center. Okay, class, I think someone is on your mic, Can you switch off your mic? So that, yeah, thanks. Okay, so A and B at the side. So the source is producing a sound outward. Okay, so A and B receive a sound with the same frequency. Okay, the distance between these two dark line is your wavelength. Okay, when the source moves towards A at a constant speed, and the source moves towards the A with a constant speed, what happened? The wavelength will be compressed. The wavelength will be compressed because the source is moving towards the A, so the length becomes shorter, so the wavelength compressed. And the wavelength compressed, what happened? When the wavelength compressed, when the wavelength is decreases, of course the frequency become higher. Frequency become higher. Based on what formula? V equals to F lambda. When the wavelength gets shorter, when the wavelength is getting shorter, the frequency will increase because speed of sound is constant. Speed of sound is found to be constant because the density of the air and the temperature of the air is same in this region, so therefore speed of sound is constant. So for the case of B, the wavelength get longer. Here the wavelength is longer, so lambda increases, so frequency going to drop. So you listen a low pitch sound. You listen a low pitch sound. Pitch of the sound is lower, and of course the speed of the sound is constant. The speed of the sound is constant. This is the phenomenon of Doppler effect. Okay, because the wavelength gets shorter and longer. So the wavelength gets crowded together in the direction of A and stretched out at B. Stretched out because of the movement of the source. Okay. So yeah. So when it gets closer, the wavelength is get shorter. Okay, to the A for the case of A, and for the B, the wavelength is stretched out. Okay, when it's stretched out, wavelength B rises, frequency drops. Okay, B equals to F lambda. When lambda changes, frequency have to change because velocity is constant. Okay. Oh yeah, like just now in the diagram here, the car moves towards you. Let's say you're standing on the left here. So when the car reaches you, you see that the frequency, the pitch is rising. The wavelength is dropping, and the car is moving towards you. Because frequency, the wavelength is getting shorter. You can see that. If you stand here, you can sense that the other way around. Lambda get longer, and therefore, lambda get longer. Lambda get longer, so frequency decreases. Frequency decreases. But for both case, what is same? The speed of sound is same. Speed of sound is constant. Speed of sound here constant. And the same thing goes for speed of sound here. Here also the speed of sound is the same. Okay. So now calculation. So according to Doppler, he found that when the source is the ambulance moving away to the left, to the right, sorry, moving to the right, you as the observer, this is the person who was standing here, observer. So the frequency the observer going to sense when the ambulance is receding, moving away from you, is V over V plus V source times frequency of the source, the original frequency of the source. Okay, maybe the frequency of the source, let's say, is the original frequency sound produced by the ambulance, let's say, is 1000 hertz. Okay, the original frequency. Then that's going to be your frequency of the source. That's your frequency of the source. When the ambulance moving away from you with a speed of, don't know, whatever speed, let's say the speed of the ambulance is 50 meter per second, then your V source will be 50 meter per second. Okay, it will be 50 meter per second. What is this V? This 2V is the speed of sound. It's the speed of sound. Okay, it's the speed of sound. So these two formulas you have to remember. Okay, these two formulas you have to remember. Okay, now let's see how he managed to get this formula. Okay, I need to explain this to you because one year they asked about the derivation indirectly. Okay, so for that, let me go to the whiteboard. Okay, you see here, you need to understand this derivation. Okay. Okay, hold on. Okay, let's say you have an ambulance. You have an ambulance here. Okay, you give out a sound. You produce a sound. The sound starts here and finish here. Let's say we take the time of a period. We take a time of one period. Okay, we take a time of one period. The wave going to come out from the source is one wavelength. One wavelength will come out from the source. Okay, we assume the ambulance is in rest, stationary. So at the time t, the one wavelength of the source will come out, L0. Okay. Okay. Now the second case is, let's say now the ambulance is approaching forward with the speed of v. Okay. Now approaching forward with the speed of v. The original position is here at the beginning. Okay. Now it's moving with the speed of v. So by the time t, we still consider time of t, one period. The ambulance from here, it might reach a new position. It might reach a new position somewhere here. Okay, let's say new position. Okay, so it stays here. Okay, this is the distance traveled by the ambulance. This is the distance traveled by the ambulance for a time of t. A period of t. T is what? One period, all considering one period. Okay, so from here to here is the original wavelength. Okay, from here to here is the original wavelength. But now, because the ambulance is already moving forward to the right, the wavelength has been compressed. This is the new wavelength, lambda dash, new wavelength. Okay, what is the original wavelength? From here to here. Okay, if I say, so from here to here is the original wavelength. Okay, this is the original wavelength. Okay, so lambda 1, lambda naught become lambda dash because of the ambulance moving forward. And ambulance moving forward, the wavelength get shrinked, shorter. Okay, now tell me how lambda 1, lambda naught, and the x related. Anyone? How lambda dash, lambda naught, x related? Lambda dash is equals to what? lambda naught minus x. Do you agree? Everyone agree? Because this is the distance traveled by the ambulance. The ambulance gets shorter. Sorry, the lambda gets shorter. So the x plus lambda dash should be the lambda naught. Okay. So what is the lambda naught? Lambda naught is the original wavelength. Lambda dash is the new wavelength. Okay. Okay. From here, the Doppler formula has been derived. Okay. Let me see here. You see here. So lambda naught. Okay. Lambda naught. You can write lambda naught as. Okay. Before we go to lambda naught, the x, the distance traveled by the ambulance. We can write in terms of the speed of the ambulance and time of the ambulance. Speed, time, distance. How the graph looks like, how the formula looks like. Speed equals to what? Speed equals to distance over the time, right? So what is the distance traveled? Is the speed of the ambulance times the time taken, Vt. Okay. So we substitute x as v times t. V times t. What is this V stands for? This V is what? This V is V of what? V of the speed of the ambulance. Remember, it's the speed of the ambulance. Okay, lambda naught. Lambda naught, which is the original wavelength. Can you use the V equals to F lambda? Speed equals to F lambda. So lambda naught is what? Lambda naught is V over F naught, the original frequency. V is here, so we can write V over F naught. What is this V stands for? This V is actually what? Anyone? This is the speed of sound. That is your speed of sound. Speed of sound divided by the original frequency is the original wavelength. Okay. This speed is the speed of ambulance. Ambulance causes the x to be x distance to travel. Okay. So the new wavelength also wavelength of the sound. So new wavelength going to be, we can use V equals to F lambda, but we say speed of sound over the new frequency, F dash. It's F dash. Okay. Understand, Okay. So let's proceed from here. Okay. So this I tried to work out here because no space. So I rewrite it back. So speed of sound over the F dash is equals to speed of sound over the original frequency minus V period. Okay, the time taken for one complete oscillation. Can you write in terms of frequency? Is 1 over the frequency, the F naught. Okay, the original frequency, F naught. 1 over F naught. Okay. So from here, we want to find F naught, F dash. Okay, what do you do? So you're going to be V minus V over what? F naught is equals to V over F dash. Okay, we flip it. F dash over V, the speed of sound, is equals to F naught over speed of sound minus speed of source. This lead to the formula. So the frequency is equals to what? Frequency is equals to speed of sound over speed of sound minus speed of ambulance times the F naught. Okay, the speed of ambulance, I just put V source, VS. From here, here itself, I put V source, VS, V source. This all our source, the ambulance. Here the source is the ambulance, it's ambulance, V source. Okay, so we got the Doppler formula. Okay, this is the Doppler formula. Okay, so the new frequency linked to the original frequency is all depend to what speed? The speed of sound and the speed of source. If the speed of source increases, the denominator get bigger. The denominator gets smaller or bigger. When Vs get bigger, the denominator gets smaller. So F dash become very huge, very high frequency. Okay, so the speed of source affects the frequency sensed by the person, all because of the distance traveled. The wavelength has been shrinked. this diagram very important. You have to remember this diagram. Okay, this diagram is very important diagram. This diagram you have to remember. Once they ask in exam about how this wavelet is related. Lambda dash equals to lambda naught minus x. X is Vs times t. Any questions from this derivation? Anyone? No questions. No questions, eh? Okay. So in A levels, they won't ask derivations, but some objective questions indirectly you have to know the derivations. If you understand the derivation, then only you can do some questions. I'll show you that the next slide. Why you need to know this derivation. Okay.
Teacher.
Yeah.
Can you pause for a while and can I copy down the derivation?
Oh, okay. You want to? It's already recording.
Oh.
So
Okay.
So later you can view, right?
Okay.
Okay. So yeah. So now tell me how this derivation going to change? How this derivation going to change if the ambulance is moving away? If it's moving away, what happened to the L dash? How this formula going to change? If it's moving away, L dash equals to L naught plus X or minus X. If the ambulance is moving away, if it's moving away, the L dash is going to get longer, right? Get longer. So now it's going to be L naught plus X. It's going to be plus X plus X. So the formula bottom here going to be plus Vs when moving away. When the source moving away from the observer, the what do you call? It's going to be plus X, and here going to be plus Vs. Okay. Okay. So later you can view this.
Question.
Yeah.
Which way is the observer in the diagram?
In the observer, because this is the ambulance. This is the wavelength. So you are standing here.
Oh, okay.
This is the observer. Okay. So you will sense a shorter wavelength. Wavelength is getting shorter for you. Okay. So tell me, throughout this Doppler effect, what is constant? What is constant? Speed of sound is constant. Remember, speed of sound is constant. Wavelength changing, frequency changing. Okay. Okay, class. So remember this formula. So this is the final one. This is the final one. I already derived you the second one. And when you move closer to the observer, you get the second one, minus V source. When you move away, then you get plus V source. In exam, you need to remember these two formula. So remember, just remember at the bottom is the V source. At the bottom is the V source. It's going to be plus minus. When you minus the bottom, when the frequency of observer increases, if the frequency of observer increases, bottom must be minus, right? So when the ambulance approaching you get closer, at the bottom you must minus. So the denominator must get smaller, so that the frequency of observer is higher. The frequency of observer is higher. So when get closer, approaching, minus source. When receding, when the ambulance going away from you, plus speed of source. Okay, these two are speed of sound. Okay, any questions? Okay, this is Doppler effect. Okay, very useful phenomena for us. Okay. So now Doppler effect can also be seen all wave, including light. Light also experience Doppler effect. There is a change in wavelength is observed. Okay. Do anyone heard of red shift, blue shift? Anyone?
Yes.
Heard of red shift, blue shift? What is red shift?
It means the light is going has lower frequency, going towards the lower frequency of the spectrum.
Lower frequency of the spectrum. Good. Yeah, lower red shift. Okay. Hey class. I need to tell you. So Doppler effect is the one of the proof for galaxy is our galaxy is expanding. You know, according to the theory, they say Big Bang theory explosion causes our universe formation, and our universe is already exploded. Now it's just in the midst of due to the explosion impact, it's going away from the explosion point, the center of the galaxy. The age of our universe is around 13.7 billion years, but because of the impact of that explosion is still there, because all the planets are moving away from each other. Okay, so scientists want to know, is it our universe is still expanding? Okay, So what they did, they, let's say this is our Earth. So from the Earth, and there is a distant star, there is one star outside here, let's say there is a star. The star, let's say, giving out a light wavelength or radiation reaching the Earth. So in the Earth, the scientists check the wavelength of this light given by the star. They monitor this wavelength maybe for 1 year, for a duration of time, maybe for 1 year or few years. They found this, the wavelength receiving from the star, this wavelength, this particular wavelength is in an increasing order. The wavelength get longer and longer. Okay, the person who are on the Earth's surface, the scientists found that from the distant star, the wavelength which is reaching to us, the wavelength is getting longer and longer. Okay, so means you as the observer, you are the observer standing here, the Earth is the observer, and the star is like the ambulance. The star is like the ambulance, okay? And it give out a light sound, and the sound, the light wave wavelength is increasing. That means the star is moving away from us or getting closer from us. And the wavelength increases. Like ambulance case, ambulance. You have an ambulance. When ambulance is moving away from you, you are standing here. Okay, the ambulance moving away from you with a speed of certain speed of source. What happened to the wavelength you're going to sense? Longer or shorter? Longer, right? You're going to sense a longer wavelength because the wavelength expand. The frequency you're going to sense is lower. Same thing happens in our star. The Earth and the star, we receive the light from the star. The light wavelength is getting longer. So what is the conclusion about the star? The star moving away from us or getting closer from us? It's moving away from us. So this phenomena, the rise in wavelength, is called redshift. Why redshift? Can anyone tell me the 7 colors, the 7 rainbow colors in order? Red,
orange, yellow, green, blue,
indigo, violet.
Violet, yeah.
Violet, good. Red or violet has a high wavelength? Red or violet has a high wavelength?
Violet.
Violet. Wait, violet or red?
Wavelength or red.
Red has a high wavelength. What is the red wavelength? We will get to know later. 700 nanometer, and violet is 400 nanometer. 400 nanometer. So maybe the star at the beginning, they found the wavelength produced by the star maybe is green color, let's say. But later, the wavelength is found to be increasing. I mean, the wavelength is going towards which direction? To the red or to the violet? The wavelength is found to be increasing. That means for the green, you're going to go increasing in order. So we say the wavelength is shifting towards red. So called red shift. It's called red shift because the wavelength is moving towards red shift. The wavelength is getting longer. Scientists, when they see the word red shift means, what they understand? What is the conclusion they understand? The wavelength is getting longer. That's the meaning of red shift. Okay, they say the wavelength they receive is a red shift. It's a scientific term, red shift. Red shift means the scientists will understand that, oh, the wavelength is getting longer. Okay, and if the scientists predicted that our Earth, the star is expanding. According to the scientists, they say there will be a moment where the star will start to shrink back. The explosion makes everything move away because of the strong gravity. The gravity going to pull all the star back. They say the star might eventually will come closer again. Prediction theory, not proven yet.
The big crunch.
Yeah.
The crunch.
Yeah, the plunge, but not proven yet. They just predicted. Okay, if the star, if let's say in maybe 200 years time, after this 200 years time, 2200 years, if the wavelength detected by the scientists is getting shorter and shorter, that means the green light change towards violet. We call that as blue shift. Call it what? So blue shift. Blue shift means the wavelength is getting shorter. If the scientists found that the wavelength gets shorter, what they conclude? The
Heading towards.
Yeah, the expansion of the star is already stopped. They are shrinking again. They're shrinking again. But it's a prediction like going to take how many billions years to shrink, we don't know. Or is it going to shrink or not going to shrink, going to continue to expand? Still is a big question mark. But whatever it is, what is the contribution of Doppler to our universe? Be able to prove that our universe is still expanding by using Doppler effect, because the light wave detected experience redshift. Okay? Redshift means the wavelength is getting longer. So according to the Doppler effect, when the wavelength get longer means the source is moving away from you, from the observer. Any questions from this slide? Okay, can understand. So remember redshift, blue shift, very important term in science. Redshift means wavelength get longer, blue shift means wavelength get shorter. If wavelength get shorter means the source is approaching you, getting closer to you. If you got a redshift means the source is moving away from you. Okay. Okay, so let's move further. The example of Doppler effect light can be seen as shown above. The galaxy moving away from Earth, observer on Earth will receive a longer wavelength than emitted by the galaxy, which evidence of the redshift. Okay, evidence of redshift. Okay, so now question. Your turn. What is the answer for this question? 1 minute for you. Doppler effect. Okay, F, the new frequency is what? Speed of sound over speed of sound plus minus speed of source multiplied by the original frequency. This is the Doppler effect. When you do minus Vs, when the source moving away, moving closer. When you put minus Vs at the bottom, if you put minus Vs, the frequency of you detected going to go up, right? So the source is moving away, moving closer. Moving closer, moving closer. Maybe when moving closer, down must be minus Vs. Okay, the denominator gets smaller so that the frequencies get higher. When something moving closer, the frequencies detected is higher. So plus Vs when the source is moving away. Source is away, moving away. Okay, use this formula. Get me the answer for this question. Okay, you can WhatsApp me. Hope everyone give me the correct answer. Give me the answer for this. Maybe WhatsApp. Okay, I receive answer C. Is it C? Yeah, this. Give me your feedback. If one of your friends says C.
So this is relative to the observer, right?
Yeah, the speed of sound relative to the medium is C. The observer measures the speed of sound emitted by the source as. Is it C? The speed of sound relative to the medium is C. Medium is C. The speed of sound measures the speed of sound emitted by the source also. It's going to be C, no effect. So the answer should be C minus V. The speed of sound relative to the medium is C. Measure the speed of sound emitted by the source as, the observer going to see the speed of sound as C plus V or C minus V. Is it the speed of sound affected? Is it the speed of sound affected by the speed of the source?
No.
Speed of sound only affected by two factors. What are the two factors affect the speed of sound?
Density.
The density of the air and the temperature. Only the density and temperature can change the speed of sound when it reaches you. Okay? And reaches you. So the speed of sound emitted by the source will be still will be
C.
Still be C. The speed of sound is not affected by the speed of the source.
So I have a question.
Yeah.
So that means that even though, like, for example, relatively, it's not different, relatively.
Relative, no, relatively not. The speed of sound still going to be the same speed.
Okay.
Okay. Speed of sound only affected by the density or the temperature of the medium only. Okay. So that's the point of this question. Speed of sound unaffected by the movement of the car. The speed of sound only can be changed if you have density change or the temperature change. Okay, so should be A. Okay, next. What's the answer for this?
Teacher, for that question, so it's not like, for example,
Yeah.
an object moving towards me at 2 meters per second, I move away from the object 2 meters per second. It's not like, so relative to me, the object is moving at 0 speed.
You are talking about the speed of the object, eh?
For example, like it goes to me 2 meters per second, I'm going away from it 2 meters per second. So that means that relatively, I see it as it does not move.
It does not move, yeah. But the speed of sound in the air is like constant.
So it's like, for example, if I go at the speed of sound and that thing is also emitting a sound, so that means I won't hear anything, right?
You won't hear anything, yeah, correct.
So that means it's not like for me the velocity is 0, not like that.
No, that's the relative speed actually.
Oh, okay, relative speed.
This is talking about the speed of sound in the air.
Or the air, not like relative to the observer.
Not using the relative concept. Okay. The speed of the sound in the air. Okay. Okay. This question, what's the answer? The source of sound moves directly towards the stationary observer. The frequency of the sound detected by the observer is different from the source frequency because what changes? The loudness of the sound increases as the source moves towards the observer. A, is it a correct fact or wrong? It's correct, right? When something gets closer, the loudness increases, right? Yeah. So A is a correct fact. It's not wrong, but never explains the frequency change, right? So A is a correct fact, but never explains the frequency change. Loudness, nothing to do with frequency. So A is not the answer. It does not explain the frequency change. Although it's a correct fact, it happens, but never explains the frequency. So A cannot be the answer. B, the apparent wavelength of the sound is longer or shorter? The apparent wavelength means the lambda dash, the new wavelength you sense. Apparent wavelength, we call it apparent wavelength. Get longer or shorter? The source is getting closer or away? The source sound directly towards the station, so getting closer. When get closer, the apparent wavelength should get shorter, right? The apparent wavelength should get shorter, the frequency should get higher. So B is wrong. It's basically it's a wrong fact. Cannot be B. The apparent wavelength is getting shorter, not longer. C, the speed of sound relative to the observer is increased. Speed of sound is unchanged. Okay. The apparent wavelength of the sound is shorter. D is the correct one. The apparent wavelength of the sound is getting shorter. Okay, the wavelength gets shorter. When the source moving closer to the observer, the apparent wavelength is getting shorter. The apparent wavelength getting shorter, so the apparent frequency getting longer, but no change in the speed of sound. No change. So answer should be D. Okay, any questions from here? Okay. Okay. Now let's see. Go one difficult one. The next one. Okay, tell me the answer for this. I want the answer for this. Everyone, please send through the WhatsApp to me. And this you need to recall back the derivation. Okay, this I really want your answers from WhatsApp. Send me through WhatsApp. or source of sound emits a wavelength of lambda, period is t, speed of the sound, speed of v when at rest. The source speed is v lah, The source move away from the stationary observer by the this small v is speed of sound, the capital V is speed of source. Yes, this is speed of sound. This is speed of the source, maybe the ambulance or what, relative to the observer. The wavelength of the sound waves as measured by the observer is, what is the wavelength of the sound wave as observed by the observer? The lambda dash, they are asking how much. Okay. So this is the derivation I show you. Okay, the source is here. The source is moving forward with the capital V. Okay, this is the original wavelength, maybe lambda. Because it's moving forward with V, this is the new location of the source after time t. After time t. Okay, so the lambda, original lambda, becomes shorter to a new lambda dash. Okay, the question asking for this lambda dash. How much this lambda dash? Which answer? In terms of period, in terms of speed of the source, V, in terms of original wavelength. Yeah. Anyone? The source sound emits wavelength lambda, the period t, and the speed v when they're at rest. The source moves away from stationary. Sorry, not closer lah. It's moving away. The one I'm drawing is moving closer. Sorry. So it's moving away. Okay, let me draw a new diagram. So like this, the source is moving away. It's moving away. The source is moving away. So this is the original wavelength lambda. Okay. The new wavelength is this, the longer one, lambda 1. The source moving away with the speed of v. The time taken is what? The time taken is 1 period. 1 period. So what is this lambda 1? Lambda 1 is equals to, how we related to lambda? How we related to lambda, the speed of source, and the period? Which answer? Anyone? Send me through WhatsApp. The new lambda get longer or shorter? The new lambda, the lambda dash, is it bigger than lambda or smaller than lambda? Because the ambulance is moving away. The ambulance is moving away, the new lambda getting longer, right? Longer. So original lambda is shorter, the new lambda is longer, right? It looks longer, right? So what is the new lambda? The new lambda is the original lambda plus with the distance traveled by this ambulance, right? The extra distance traveled by this ambulance, right? So lambda dash should be what? Lambda plus the extra distance traveled by this ambulance, right? X. So it should be lambda plus X. So what's the answer should be? How do you get this X? What is the extra distance traveled by this X? What is the extra distance traveled by this X? What is the extra distance traveled by this source? The distance traveled by the source, how much? Distance traveled by the source. Is it speed of sound times the time or speed of the source times the time? Small v times capital T or capital V times T? Small v is speed of sound. Small v is speed of sound. Capital V is speed of source. So tell me, the source is moving away for a distance of x. Okay, so which speed going to affect the distance of x? The speed of sound or speed of the source? Which speed affects the x? Speed of sound or speed of the source? Anyone? Because the source is moving away, it increases the distance of x. Increase the distance of x. So which speed affects the distance moving away? Speed of sound or speed of the source? Should be? Anyone? Should be speed of source one. Speed of source. If the source moving 5 meter per second, let's say the source moving 5 meter per second, the period is 2 seconds. Okay, let's say the period is 2 seconds. For a period of 2 seconds, what is the distance it should travel? What is x should be? 5 times 2, right? 10 meter. It should travel 10 meter. What? So not for the 2 seconds, what is the distance traveled by the source? Not you're going to times the time with the speed of sound. Speed of sound is what? 300 plus meter per second. 300 meter per second. So if the source moving forward in time 2 seconds, what is the distance traveled by the source? You put speed of sound times the time. It's going to be 600 meter. No, that is not the distance traveled by the source, right? Distance traveled by the source, nothing to do with the speed of sound. It's nothing to do with the speed of sound. It's something to do with its own speed of source. Speed of source times the time is the extra distance traveled by the source. Let's say you are walking. Okay. Let's say the duration time is 2 seconds. 2 seconds. Okay. You walked for a distance of x meter in 2 seconds. Which speed determines how far you travel forward? Your speed or the sound speed? Your speed, right? Depends on your speed one. If you are 10 meter per second, 10 meter per second, after 2 seconds later, what is the distance you travel forward? 2 times 10 last, so 20. So in this diagram, the extra distance traveled by the source x is actually v times t. The v must be speed of the source. Must be speed of the source. So therefore, the answer should be what? Should be C. Should be C. The answer should be C. Cannot be A. A is speed of sound. Okay. Okay. Many of you give me A. Try to rethink back. Cannot be speed of sound. It should be speed of source. Okay. The extra distance is the speed of source. Any questions from here? Okay. This question you only can be able to do if you know the derivation. If you know the derivation, the x is vt. The extra distance travel is vt. The v is speed of source. It's not speed of sound. Okay, any questions from this question? Okay, can understand, Okay, class. So, yeah. Before, I don't want to start with electromagnetic wave yet. I go back to this word file. Okay, this is the word file, the notes about wave. We done the progressive wave. We done about period, frequency, amplitude. We done about the phase difference. We done about the intensity, and it's a short notes. Then we got some questions here for you to do in the notes also. You can give a try. Today we talk about Doppler effect. Doppler effect is a change in observed frequency of wave when the source or detector move relative to the transmitting medium. And this is the two formulas you have to remember. Okay, give a try this question. Hope you get these 3 answers. 1 minute for you, class. Come on, give a try. The siren of an ambulance emit. Okay, let me expand this. Okay. So do the working. The siren of an ambulance emits sound with a frequency of 700 Hz. You are standing on a pavement. If the ambulance drives past you at a speed of 20 meter per second, what frequency will you hear when the ambulance is approaching you? So what formula do you use? Okay, what formula do you use? So the ambulance is approaching you. Okay, the ambulance is approaching you. Approaching means when approaching, the new frequency is equals to, how's the formula looks like? This is your speed of sound. Yes, speed of sound also. You plus or minus speed of source. This is your original frequency. Plus or minus. Approaching. You are standing here. So should be?
Minus.
Minus, good. It should be minus. So this the formula must come to your mind. So put all your values. Remember, these two are speed of sound. These two are speed of sound. So speed of sound should be given by them. Do they give the speed of sound? Oh, speed of sound is down there, 340. So 340 So here 340 should be minus. That's the most important. Minus by speed of source, which is 20, times the original frequency, which is how much? 700. Yeah. So 700 will give you this 744. The frequency rises 7,744 hertz. And B, check the ambulance is driving away. Driving away, you should know the F dash, the new frequency must drop down from the original frequency. So therefore, down should be plus. Should be plus the Vs. Okay. So remember this one. Then you get this answer, 661 hertz. Okay. So it's calculation Doppler effect. There is no not a challenging one. Just you need to know, is it plus or minus at the bottom. The challenging one is the derivation. When just now the question asks, is it plus a VT or minus VT? That you have to visualize that. What V? Is it speed of source or speed of sound? Should be speed of source, the extra distance travel. And that could be challenging. Okay. Okay. When I'm teaching this, one interesting question come to my mind now. I saw this in one website about Doppler effect. Okay, let me ask you that question to you now. Okay, the question they said is this. Okay. Okay, let me ask you. A scientist from the Earth find the frequency emitted by the sun. Okay, a frequency emitted by the sun. Okay, they found that two different frequencies have been observed from the sound. Two different frequencies has been observed from the sun. Okay, two different frequency. One is maybe I give a value maybe higher 720, another one maybe 680. Two different frequency has been observed from the sun. So the question they ask, what scientists conclude about the sun when they receive two different frequencies?
Oh, the orbit of the Earth is not a perfect circle.
The orbit of the Earth is not perfect circle. Then why you got two different frequencies?
One is from the furthest length from Earth to Sun. One is from the shortest point from Earth to Sun.
Okay, the distance traveled by the light, is it going to affect the frequency of the light? Is it the distance from where the light reaches the Earth? Is it affects the Doppler effect? Use the Doppler effect. What frequency shortest? Anyone? Two frequency has been observed from the sun. Use the Doppler effect. When you conclude, use the Doppler effect. Okay, class. I think mic. There is someone on the mic. If you're willing to answer, you can on it. If you're not, you shut down. Yeah. Yes. Anyone? If you have answer, you can on the mic and tell me. Two different frequencies. If the frequency is longer, means the source is moving away from you or moving closer from you. When the frequency is higher, means the source is moving away from you or moving closer from you. Moving closer, right? And move closer, you get a high frequency one.
Yes.
So the sun as the source is moving closer to you, produces a 720. Then 680 happens when the sun is like moving away from you. That means the scientists conclude that sun is rotating.
Oh.
That's the answer given. The sun seems to be rotating. That's why giving a two different frequency. The side where rotating here, this side, the source is like moving, getting closer to you. So it gives a longer wavelength, greater frequency.
Okay.
This side, which is moving away, give a shorter frequency. So two range of frequency, they conclude sun is rotating through Doppler effect. You got idea, eh? Hey class, good. So this is today's class, something new you never learned before. It's Doppler effect. Okay. So what is Doppler effect? Doppler effect is the change in observed frequency of a wave when a source or detector move relative to the transmitting medium. The source is moving or the detector moving, you will get Doppler effect. But in your syllabus, observer not moving, only the source is moving. You get that's only in your syllabus lah. If the observer is moving, the formula is going to change, which is not in your syllabus. The formula is only about the source. So your syllabus is only source moving. Okay. So that's the Doppler effect. What is the use of Doppler effect? Universe expansion, speed trap. Speed trap also they use Doppler effect. You know the device they use hold in your hand is actually works based on Doppler effect. Okay. They shine a radio wave to your car when you drive. The radio wave going to hit your car and bounces back to the receiver, so they can see a different frequency. Okay, if your car is approaching towards you, the frequency they're going to detect going to be higher than the original frequency. So the device is going to calculate the speed of your car. From there, they get to know what speed you are traveling. So Doppler effect is useful for the speed trap. Okay. Okay. So we have another one part electromagnetic wave. We do that tomorrow. Any questions so far? No questions. Okay, class. So I stop here. So tomorrow we start with the electromagnetic wave. Okay then. Thanks.